Okay, welcome back to our semester-long sequence of videos on basic circuit analysis. This is lesson 21, RMS value and complex power. Alright, well I'm going to start with RMS value. And if you see there I've got value and not power, and that's because in general voltages have RMS values, currents have RMS values, power can also have RMS values. So we're going to keep this general. We're going to talk about the RMS value, not necessarily RMS voltage, RMS current, RMS power. And I would be surprised if you've never heard the word RMS at this point in your reading, or it comes up just in engineering in general. You'll hear RMS value sometimes. So you might also hear the word effective. So I want to start here. You might hear the word effective value. All right, and I want you to consider the following experiment. Okay, suppose we have, we'll say a voltage source just to be concrete here. Let's say we have a voltage source of, let's say V of t equals some maximum, right, some amplitude Vm, and it's just a sinusoid, we'll say cosine, of some frequency omega t. Okay, so this could be a sine wave, this could be an exponential, complex exponential, but the idea is that it is a sinusoid of frequency omega, and it has an amplitude Vm. Okay, now if I connect that to a load, okay, I'm going to make the load a resistor, because what I want to bring back here is the concept of average power. Okay, and the average power supplied from the source to an inductor would be 0, and a capacitor would be 0. But for a resistor, the resistor only absorbs power, and so its average power cannot be 0. And from the previous video, you should know that the average power in that resistor can be written as 1/2 the maximum squared times the cosine of the angle between the voltage and the current. Okay, and with a resistor, of course, the voltage and the current are in phase with one another because the resistor is purely real, and so the cosine of 0 is 1, and so the average power absorbed by that resistor, or equivalently supplied by the source, is the amplitude of the source squared. So, sorry, there's a divided by r here, over 2r. Okay, this is the average power, and I quickly divided by r here. I just want to point out from the previous video we said that the average power was 1/2 the maximum of the current, the maximum of the voltage, times the maximum of the current, or the amplitude, times the cosine of the angle in between those guys. And of course the current is the voltage divided by the resistance. So this is 1/2 Vm squared over r, and then separately times the cosine. So that's why that divided by r came about there. Anyway, this is the average power absorbed by that resistor. So now let me ask you the following question. Consider now a DC circuit. Okay, everything was so nice with DC. We didn't have to worry about average powers and all this stuff. So nice. All right, let's consider this DC circuit, and we're going to make the load resistors the same in both experiments here. Okay, so RL, and we're going to call this thing V Rms. All right, well, question, what must V Rms be so that the resistor in the DC circuit absorbs the same power as it did on average in the AC circuit. I'm going to write that down actually. What must V Rms be? So RL in the DC circuit absorbs the same power as it did on average in the AC circuit. Now there's no average in the DC, of course, because this is not a time-based idea. Right, but you see now where the word effective comes from? Effectively then, if this DC voltage source is supplying the same power as it is here on average, okay, then effectively, as far as power is concerned, effectively these two circuits you could argue are equivalent in that sense, in the power sense. Okay, so let's figure it out. Well, back in DC, when things were nice and easy, the power absorbed by that resistor was V squared over R. So this would be V Rms squared over R. Okay, so let's set, now we want to answer this question, so let's set these two powers equal to one another. So we get Vm squared over 2R equals V Rms squared over R. Okay, and R's cancel, and I can take the square root, and I'll just keep the positive square root, and I get that the V Rms is the amplitude of the AC wave divided by the square root of 2. And this holds only because of a sinusoid. It's a sinusoid. Okay, so I just want to emphasize that. We started with a sinusoid here. So this is the RMS value of a sinusoid. So in this class, as previously has been discussed, we're only going to worry about sinusoids. And so this result holds only for sinusoids. You will not have to know the RMS value of any other wave. Okay, so just know that if you take the RMS value of a sinusoid, you're going to take the amplitude of the wave and divide it by the square root of 2. Okay, similarly, if we had a current waveform, okay, the current waveform would be the amplitude of the current divided by the square root of 2. And when you divide by the square root of 2, that's the same thing as multiplying by 0.70 approximately. And remember, then the interpretation here is that this AC circuit, on average, is supplying the same power as this DC circuit is. So the power calculations end up being kind of equivalent in that sense. All right, let me give you a second interpretation of RMS value before we move on to complex power. I'm going to delete this, pause the video if you feel the need. So you see we were kind of dealing with an average power in the DC sense, right? So we wanted the DC equivalent of the AC's average power. So let's look at a voltage or a current sinusoid, right? We'll just keep it general for now. We won't say this is a voltage or a current. We'll just say it's a sinusoid. Okay, and we'll call this x of t or whatever. But what's the average value? Yeah, okay, let's call this v of t. Let's say that's the voltage. Well, what's the average value of this waveform? Okay, it has an amplitude of a, or let's say Vm. minus Vm. What's the average value of this thing? You know that? The average value of a sinusoid is, of course, 0, right? Because it's positive as much as it is negative. So yeah, it's 0. So the average value really doesn't tell us much in terms of how much power that thing is carrying or how much power that thing's going to be supplying. Instead, if we want to talk about average, we might be interested in the average of this waveform in an absolute sense, meaning not taking into account the sign, S-I-G-N, of this thing. So consider this to be Vm and also this point to be Vm. Then what would be the average value if you consider everything to be positive? Okay, well, you know, of course, the absolute value function, right? But the absolute value function, we're going to have to take an average of an absolute value. That's going to be difficult because the absolute value function is what we call non-analytical, meaning it doesn't have an integral and it doesn't have a derivative, a well-defined one anyway. So another choice we have to get rid of the negatives when we take the average value is to square the waveform. So let's again suppose that Vt is a sinusoid. So it looks like this. We'll say its phase is 0. And let's square the waveform. Cosine squared omega t. All right, now when we square it, we get something that looks like this. Okay, and this amplitude of course is Vm squared, but of course we've gotten rid of all of the negatives. And so now we can take the average of this thing. Okay, let's take the average of this guy now, and we don't have to worry about the negatives canceling with the positives. All right, and another word for average. So let's back up. So first of all, we squared this thing, right? We squared our waveform to get rid of the negatives. We'll just write that down. We're going to take the average now. Another word for the average is the mean. Right, so we're going to use the mean value theorem to take the average of this thing. So now we've got the integral of, now if this thing had a period t, right? T is 2 pi over omega. This thing has a period t, and when you square it, right, the negatives become the positives, so this is actually 1/2 t. Right? Now if I want the average value of this thing, why not just get the average value over one period? Right? The average value of a periodic signal is just the average value of over one period. So let me integrate this thing from 0, now we'll say to t. And then let me divide by that time frame, 1 over t. Okay, this is the mean value theorem from calculus. And I'm integrating the square of this thing. So this is Vm squared cosine squared omega t. Alright, so what we need to do here is bring out the Vm squared. Okay, that's a constant. And then we're going to apply a power reducing formula from trig. So the cosine squared of omega t, that is 1 plus cosine of twice omega t over 2 dt. Alright, so if I integrate that, then I've got the 1/2 integrates to 1 over 1/2 t, right? And then the 1/2 cosine of twice omega t, that integrates to 1/2 or 1/4 over omega sine of 2 omega t. You can check yourself. If you take the derivative of this thing, the sine turns into a cosine, the 2 omega comes down and cancels with the omega here and cancels with the 2 here, leaving 1/2. So that's correct. And so let me plug in capital T, which is the period. So this is 1/2 t plus. And when I plug in t here, I've got 1/4 over omega sine of 2 omega. Remember, omega is 2 pi over t. So this is 2 pi over t times t. Okay, and then when I plug in 0, I've got 0 here, and the sine of 0 is 0. So these t's cancel, and the sine of 2 pi is 0. So this gives me, this is all 0 here, Vm squared over 2. Wow. So this is the average value of the square of the wave. And but I squared it, right? So I squared this thing initially. So now this is in units of volts squared. Let me bring it back down to our original scale of volts. So let me take the square root now, because I squared it initially. Now let me get back. So now we have the square root of Vm squared over 2, which is Vm over root 2. This is exactly what we saw V Rms to be. So you see, we started with here's our sine wave, right here. Okay, and we wanted to know what was the average value of this thing in an absolute sense. Okay, so we squared it to get rid of the negatives. Then we took the mean of this thing. Then we took the square root to get back to volts instead of volts squared. And yes, if you haven't guessed already, RMS stands for root mean square. Right? So the RMS value of a voltage signal is the square root of the sinusoid, the square root of the mean of the square of the sinusoid. There you go. And in general, for any signal, not just voltage, but current as well, power, any sinusoid, any periodic signal really, this is not limited to sinusoids now, we're going to take the square root of the average of the square, and that is going to give us the RMS value. Okay, so you have two interpretations with the RMS value. The first one was the one that we deleted already. It was the RMS value is the equivalent DC source that supplies the same power as the AC source does on average. The second interpretation of RMS value is the average value of your signal in an absolute sense. Alright, let's move on to complex power now. Okay, again recall that the average power absorbed by a load or delivered by a source is 1/2 the amplitude of the voltage across the element times the amplitude of the current through the element times the cosine of the angle in between the voltage and the current waveforms. All right, now I'm going to get a little slick here, and we're going to write the 2 in this thing as the square root of 2 times the square root of 2. All right, so if you take the square root of 2 and you multiply by the square root of 2, you get 2. So I'm going to write it like this. You'll see why in just a second. All right, well, why did I do that now? It's because Vm over the square root of 2, that's the RMS voltage across the element, and Im over the square root of 2, that's the RMS current through the element. You see what's happening here? Alright, now, this product of V Rms with I Rms, this guy, we'll call this S. Your book uses S. So we'll write this as S cosine of theta V minus theta I. And the idea here is that S is called the apparent power. Again, S is the RMS voltage times the RMS current. It's the apparent power because if we're thinking in terms of DC, it's apparent that the power should be the voltage times the current. Right? So here we go. We've got a voltage times the current. We're going to call that apparent power. And in industry, in applications, this is not written as watts. This is just kept as voltage amps. So this is measured in VA, not watts, W. And that's to distinguish apparent power from average power. Okay, so we're going to just keep this as V times A. And yeah, we know that that's a watt, but we're not going to write it as W. All right, now, this guy here, cosine of the difference in the voltage and current angles, this guy is called the power factor, PF. PF is the power factor. PF equals cosine of theta V minus theta I. So this is unitless because when you take a cosine of something, you get out a unitless number. Think back to trig. Cosine is a ratio of 2 lengths of a triangle. So if you take the ratio of two things, then you get a unitless number. All right, and PF, the power factor, is also then, notice, if I divide by S, it's the average power divided by the apparent power. So that'll be important in just a little bit. Some good stuff here. Let's look at an example now. Okay, I guess I'll squeeze in the example at the bottom. All right, we'll say a series connected load draws a current I of t equals 4 cosine 100 pi t plus 10 degrees amps when the applied voltage is V of t equals 120 cosine 100 pi t minus 20 degrees volts. Find the apparent power and the power factor of the load also what circuit elements form the series connected load. Alright, so I am going to erase the top. Well, no, let's squeeze it in. Let's squeeze it in at the right. I'm going to write it in red. Okay. So first of all, the apparent power, S, is V Rms times I Rms. So look here, I've got my V is what it's got an amplitude of 120 volts. So the RMS value there is 120 over the square root of 2 volts. And the current has an amplitude of 4 amps, so its RMS value is 4 over root 2 amps. Okay, so the 120 times 4 is 480 divided by 2 is 240, and yet we're going to say that this is, what are the units? Volt amps, not watts. I'm just going to write that as volts amps. Power factor, okay, PF, is the cosine of the angle in between the voltage and the current. So the voltage is minus 20 degrees. Okay, the current is plus 10 degrees. So we're going to minus 10 degrees there. And so if I do that calculation, I get 0.866. And we're just going to note that the current then is leading, see the 10 degrees, the current is leading the voltage. Current is leading the voltage. Okay, that'll become apparent very soon when we look at the series connected load circuit elements. Alright, so let us calculate the load voltage now, or the load impedance, now. Z, the load impedance, is, again, from Ohm's law, V over I. So V is 120 angle minus 20 degrees volts. I is 4 angle 10 degrees amps. So when we do that calculation, we get Z equals 30 angle. So again, the magnitudes divide, right? So that's what we get 30. And the angles subtract minus 30 degrees. And this is ohms. Okay, now if we put that in rectangular form, okay, we get 25, a real part of 25.98, and an imaginary part of minus J 15 ohms. Right. Notice here again, this minus 30 degrees, right? Cosine of that minus 30 degrees, that gives you the power factor. So the power factor shows up again here. Alright, well, we have a series connected load, so that means Well, there's going to be a resistor that's going to give us the real part of the load. So this load must contain a resistor of 25.98 ohms, right? And it also must contain a capacitor. And I know it's a capacitor because this is a minus J, 15 ohms. So what is the capacitance? Well, remember, do this in blue, the impedance of a capacitor is 1 over j omega c, which is minus j times 1 over omega c. So that means 1 over omega c must be 15 ohms, right? Omega is 100 pi. The frequency is 100 pi here. So if we solve that for c, plugging in 100 pi, we get that c must be 212.2 microfarads. So here is our load. And again, the voltage across a capacitor, we saw this a couple videos ago, lags. The voltage lags the current. So that's what we saw here in our power factor. The voltage is lagging, the current is leading. Of course, we know that that's from a capacitor because a capacitor has a negative imaginary phase, negative imaginary part, right? The voltage lags in a capacitor. Alright, so we're finally ready for complex power now. And the best way to do it is just to dive right in. So we're going to define complex power as this. It's bold in your textbook, but to show it on the screen here, I'm going to give this some little vertical lines here at the edges of the S. So this is a bold S, and this is complex power S, and I'm just going to start by defining it. It's 1/2 V times I complex conjugate, and you're going to see why it will be defined like this, because this is actually holding all of the information of the power in this little complex expression. So again, I'm going to use this trick where I'm going to let the 2 be the square root of 2 times the square root of 2. So this will be V over the square root of 2 times I complex conjugate over the square root of 2. And these are phasors now, right? V has a magnitude and a phase angle, and I has a magnitude and a phase angle. So this V over square root of 2, I'm going to still write it as V Rms, but we're just going to note to ourselves that this V Rms is got also a phase angle to it. And I complex conjugate over the square root of 2, that also, write that as I complex conjugate Rms, and that has a phase angle associated with it. So if I do that multiplication, right, this is V Rms, so this is now I'm going to break it down into its magnitude and phase, right? So V Rms, this is the magnitude, this is the amplitude over the square root of 2 part, and this is the angle, times, I'm going to break this guy down, Rms complex conjugate, well, that's its amplitude over square root of 2, right? So that's I Rms, and then when you take the complex conjugate of a complex number, that is minus its angle. Right, so this thing now is V Rms, so this is the magnitude over the square root of 2, times I Rms, again the magnitude of the current over the square root of 2, times the angle difference. Right? So this should look familiar. This here, again, is S without the bars. So And this here, this is the power factor angle, right? That was the thing that was inside the cosine when we defined the power factor. So you see already why this expression here, again, this is the complex power, why this expression here is important. It's containing the apparent power and the power factor. So in fact, the magnitude of the complex power, that's this thing, that's S, is the apparent power, and the angle of the complex power is the power factor angle. Okay? And what we're going to need in a little bit here is this expanded in rectangular form. So we can use Euler's equation to expand this in rectangular form. This is V Rms I Rms times the cosine of theta V minus theta I plus J times V Rms I Rms sine of theta V minus theta I. Okay, so we're going to need that in just a little bit. But yeah, again, here's complex power in the box. Okay, and notice the relationship we get here is that the magnitude of complex power is the apparent power, and the phase of the complex power is the power factor angle. Now, from Ohm's law, okay, of course, the impedance, the voltage current relationship across and through an impedance is related to Z by Z equals V over I. Okay, and this is Vm, right? This is a phasor, so Vm angle V over Im angle I. So again, V has a magnitude and a phase, I has a magnitude and a phase, and if I divide the numerator by the square root of 2 and the denominator by the square root of 2, let me do that, I haven't changed the fraction. Right? If you do the same thing to the numerator that you do the denominator, you do not change the fraction. So the reason I did that, of course, is because Vm over the square root of 2, right, is V Rms, and then the angle V, that's what we're calling the phasor RMS. So this is V Rms divided by, and then down here we have I Rms, phasor. So Ohm's law also holds for these RMS phasors. Okay, so we see that V Rms equals Z times I Rms. Okay, so great. Now, if I plug, we'll call this this guy here, this is bold S, call that equation 1, and we'll call this equation 2. If I plug equation 2 into equation 1, what I see is that the complex power is equal to Z times I Rms times I Rms complex conjugate. So when I take a complex number times its complex conjugate, I get the magnitude squared. Magnitude squared, so the magnitude of this thing is just that amplitude over the square root of 2. So this is Z Im over the square root of 2. all of that squared. So this is Z Im squared over 2. And similarly, if I rearrange equation 2 for I Rms and I plug that into equation 1, what I'll see is that the complex power is, of course, let's do it. So if I solve this for I Rms, this is V Rms over Z. Okay, so then in equation 1 I have V Rms times V Rms over Z complex conjugate. Okay. And this turns out to be V Rms magnitude squared over Z. Complex conjugate. Okay. Now, since the complex power is a complex number, okay, it has a real part, we'll call that P, and an imaginary part, we'll call that Q. Mind your P's and Q's. And if I compare it to this thing here, okay, this is also equal to I Rms times Z. Z has a real part, call that R for resistor, and an imaginary part, X. Right? Rms squared. Okay, so now we compare these guys and we see P is the real part of the complex power. Okay, we're saying P is the real part of the complex power, and that is equal to if we distribute the I squared Rms in, this is I squared Rms times R. Okay, Q is the imaginary part of the complex power. If we distribute this in, that is I squared Rms times X. So P is the average or real power, and it depends on the load's resistance, R. Q is dependent on the load's reactance, X. And so this is called the reactive power. Okay, now if we compare this guy, okay, call this equation 3. So let us compare that guy with here. Okay, we notice that P, okay, the real part of the complex power, is equal to V Rms I Rms times the cosine of the angle difference. Right, so we're just comparing 3, and we'll call this equation 4. Comparing 3 with 4. And Q, the imaginary part of the complex power, is V Rms times I Rms, okay, times the sine of that power factor angle. Okay, the real power P is the average power in watts delivered to the load. It's really the only the only useful power, and that's because the reactive power Q, okay, it's a measure of how the inductors and the capacitors are exchanging energy with the source. Okay, remember, the inductors and the capacitors, they store energy, so there's this energy that's going back and forth And so the net energy there is 0. So that's why the P is the only useful power here, the real part of that power. Okay, so if Q equals 0, okay, then there is no reactive power, and the load is purely real, so the load is purely resistive. And so if that's the case, then the power factor angle, okay, the voltage and the current have the same angle in a resistor. So the power factor is 1. The cosine of theta v minus theta I is 1. If the reactive power is less than 0, okay, so the Q equals 0, this is resistors. Power factor equals 1. Okay, if Q is less than 0, this is for capacitive loads. So capacitors. Capacitive loads, right? And so you have a leading power factor. Okay, because the current is leading. And then when Q is greater than 0, this is inductive loads. And you have a lagging power factor. Okay, there's a lot here, and let's summarize all of this. And you're going to see, again, why complex power is important, because this one brief equation that we started with, it turns out that this thing is containing all of this information just in this one little piece. So I'm going to delete this. If you need to pause the video, please pause the video. Alright, so let's summarize. The complex power, we're going to say, is this bold S. That has a real part and an imaginary part, i.e. it's complex. You see where we get the name, right? And we're going to write that as V Rms, which is a phasor, right? It has a current, it has a waveform, excuse me, it has an angle, angle is what I want to say there, it has an angle and an amplitude, right? And times the RMS, current complex conjugate. Now, the apparent power, okay, and again, this is a summary. The apparent power is this non-bold S, and that is the magnitude of the bold S. Okay, that is the square root of the real power squared plus the reactive power squared. And I guess I should define those. The real power, again, is this the real part of bold S. That's just what we're calling P. And the reactive power, okay, that is the imaginary part of this bold S. That is what we're calling Q. Okay, and from Euler's equation, the real part of a complex number, okay, that's the magnitude, which was the apparent power, times the power factor angle, the power factor. Right? And the reactive power, again from, this is Q, from Euler's equation is the magnitude, which is the apparent power, times the sine of the power factor angle. And again, that power factor is just PF. That's the real power, or excuse me, that's the cosine of the angle between the voltage and current waveforms. So again, everything is contained in the complex power. If you have the complex power, you can get all of these four things. Okay, so let's look at an example. The voltage across a load is V of t equals 60 cosine of omega t minus 10 degrees volts. And the current is I of t equals 1.5 times the cosine of omega t plus 50 degrees amps. We're going to find the complex power and apparent power. Okay, the real and reactive power. And the power factor. Okay, so we're going to find all the, based on just the voltage and the current measurements. Alright, so the RMS values might come in handy here. Let's just note that the RMS phasor, so I've got an amplitude of 60, right? So the magnitude of the RMS is 60 over square root of 2, and the voltage has a minus 10 degree angle. Right, so there's the RMS value for the voltage, and the current similarly is 1.5 over square root of 2 angle 50 degrees. So the complex power, which we said was V Rms times the complex conjugate of I Rms. Okay, we can do that multiplication. We get 60 times 1.5 is 90, but then over 2, so that's 45. And then the angles add, but when we take the complex conjugate of I Rms, this is going to be a minus 50. So we've got a minus 10 and a minus 50, so that makes minus 60 degrees, volts, amps. Alright, so that's part of our answer, right? That is the, again, complex power. Now if we want the apparent power, everything we can get from this guy. So the apparent power is what we're calling S. That is the absolute value or the magnitude of bold S. So that is just 45 volt amps. Okay, so for the real and reactive powers, okay, we're going to break the complex power down into its real and imaginary parts. So we're going to write the complex power as 45 cosine of negative 60 degrees plus j 45 sine of negative 60 degrees. So this comes out to be 22.5 minus j 38.97. So the real power, P, is 22.5. And since this is a real useful power, we're going to say that's watts. Okay, and Q is the reactive power, that is minus 38.97. We're going to keep that as volt amps. Sometimes you'll see an R for reactive there. Volt amps reactive. VAR. Okay, so the power factor here, PF, that's the cosine of the angle in between these two guys. So that's minus 10 degrees and 50 degrees. So it's minus 10 degrees minus 50 degrees. So that comes out to be 0.5. And we'll say this is leading. The current is leading. And that is because Q is negative. So we'll say this is a leading power factor angle. Okay? And so we have everything we need.